Test. Okay, good evening. Let's get started. All right. Here is the question that we didn't quite finish from previous lecture. So let's finish that. Okay, so basically, it's a question of a double integral. Okay. You can try really different approach. One of the approach that we tried from previous lecture is you separate this region R into two different regions, R1, R2. And then you can integrate over R1, R2 separately, okay, and then to get the integral. So we also started another approach is to use the change of variable approach. For change of variable, essentially you try to transform this region R, okay, into a slightly more regular or more simpler looking type of region. So when you do the change of variable in this case, you can actually try different approaches. But what we did is we let u equal to x plus y. So basically let u equal to this and let v equal to y minus 2x. So this is basically the line here, y minus 2x equal to 0. Okay. Then we solve for x and y. Okay, based on these two equations right here, we can get x equal to 1/3, u minus v, y equal to 1/3, 2u plus v. So the solution to x and y based on this is that. Okay, so now you get a function. You get a function x in terms u and v. You also get a function y also in terms u and v. So you can construct that coordinate transformation vector, right? Remember, so for the purpose of the Jacobian. Now, before we calculate Jacobian, we can take a look at together. So how this region R transform into the coordinates u and v? How is that making it simpler? I think we demonstrate this. First of all, the boundary x plus y equal to 2, because your introduction of u become u equal to 2. So if this is u, this is v. So u equal to 2. So this is u equal to 2. And the other boundary y equal to 2x, which is y minus 2x equal to 0. With the introduction v becomes v equal to 0. So v equal to 0 essentially is the horizontal u axis. Okay. Right, that's v equal to 0. So how about the last boundary, y equal to 1/2 x? Okay. So y equal to 1/2 x. Okay, we need to transform everything into u and v. You already obtained the x and y in terms of u and v at here. So we can substitute x with 1/3 u minus v, substitute y with 1/3 times 2u plus v at here. So you get 1/3 2u plus v equal to 1/2 times 1/3 u minus v. Right, that's the expression xy based on the introduction of u and v. Then you can simplify this a little bit. You get u plus v equal to 0. So the original boundary y equal to 1/2 x in the xy plane. You got a new boundary, which is u plus v equal to 0 in the uv plane. And that is a curve. That's a straight line, okay, in the uv plane like this. And this is -2 at here. So the three red boundaries give you the new region R prime. Okay, you can call this R prime, and that's your double integral region R prime, right? So that's much easier to deal with. It's a very regular triangle. Okay, so now you can let's try the Jacobian in here now. Okay, we already got the vector transformation matrix. Okay, so the way to use Jacobian is you need to calculate the determinant of Jacobian, which is basically determinant of this 2x2 matrix, partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. So here's your x, here's a y. All right, this is your x expression, this is your y expression. So you calculate the derivatives, okay, of the 4 derivatives. You get 1/3, negative 1/3, 2/3, 2/3. The determinant, you get 4/9. That's a positive number. So this times this minus this times this. Okay. So finally, your integral, okay, double integral, let's say, for example, if we're integrating f of x, y, so you replace x with the corresponding function x of u and v, replace y with the function of u and v. So whatever the function it is. So we're just doing a general here. And then and then the determinant of the Jacobian is plugging over here, du, dv. Okay. And then plugging the limits for u and v. So again, for limits for u and v, you follow exactly the same procedure as you did for x, y coordinates. So if I decide to do the du first, then if I decide to du first, then what do? I actually will draw an arrow line in the u-axis direction. First contact give me u mean. Second contact give me the u max. U mean is on this line u. What's going? This line here is u plus v equal to 0. So that's u mean must be negative v, right? So negative v 2. This boundary here is 2. Okay. That's the u limit. And v is you sweep these arrow lines from the minimum here to here. That's from -2 to 0. And that's how you find the limits for u and v. Right, this is much simpler. So you just have to do one region. And of course, don't forget to replace this term with 4/9. And let's see how you calculate. If you got a function here, then you can calculate the rest of the double integral. Okay. So this is a demonstration of using change variables instead of piecewise integrations, right? Separate R into R1 and R2. Okay. So what I want you to practice is this, okay? So in this case, I chose U to be this boundary, V to be this one. Okay. So I want you to try a different change of variable. So you can still use U is this, but I want you to try the V as Y equal to Y minus 1/2 X. So basically, the V at here, okay, is based on this boundary. Okay. So this is one way, right? And you can also try another one that U equal to Y equal minus 2X and V equal to Y minus 1/2 X. Okay. So both of these two are also valid change variables. So I want you to try this, and you can also plot what does the region R prime look like if you use this change variable, and what does the R prime look like if you use this change variable. Okay. So certainly it won't be a triangle like this, right? But it's still going to be a triangle actually. Right? So either way, it will be simpler calculation than the traditional approach. Okay, so that's change variable, right? The gist of change variable is you want to make things simpler, not to make it more complicated. If you end up with a more complicated situation, then you might actually doing something wrong there. All right, so let's continue now. Let's look at some applications of a double integral. Any questions on change variable? All right, so double integral, we'll learn triple integral after double integral, and there's also applications of triple integrals. The triple integrals application, a lot of them are actually based on extension of double integral. So let's spend a little bit more time on the application double integrals. Okay. So first, let's take a look at the easy one. How shall we calculate the area of a region R? So let's say you have a region R given in the XY plane, and you're required to calculate its area. If it's a regular region, if it's a triangle, it's a circle, you can certainly calculate using a pre-derived formula. Okay. But if area region is not so regular, then we need to use integral approach. So this is where double integral will come into picture. And if you recall the formula for double integral, is you integrate this function f over a certain given region R. Right, this is a general double integral formula. Now, if I let the integrand function equal to 1, okay, so f of x, y, take a value of 1, then the double integral becomes this. So you're integrating just constant number 1 over the region R. So then what you're doing here is essentially you have an integral and then you have a d, which followed by the a here. And the a, right, in essence refer to the area. So basically, if you recall, dA is a small area, right? So if you integrate R of dA, so you're adding all the small area up over this region R. So then you get what? You get basically the total area of the region R. Right? So that f of x equal to 1 naturally give you the total area of the region R. So then how do I get this area then, right? Then all you need to do is follow exactly the same approach. You can use Cartesian or polar, okay, or change a variable, however you want to choose, and find the limits of the associated coordinates system, and you can get the double integral, right? Which will give you the area of this region R. That also actually says something. Remember, I said when you integrate d anything, okay, when you integrate d anything, what do you get? You get anything out of it. And this is the same thing, even though this is two integrals, but you're basically integrating something out here, you get back this basically. In this case, you get the area. Okay. So that's the first application, to use double integral to calculate the area of a certain region R. Second application is also very straightforward, is to calculate the mass of a thin plate. Notice the keywords here, the thin plate. Thin plate basically means we will neglect the thickness of the plate. Okay, if it's thin enough, right? So we don't consider the thickness. If you don't consider thickness, then the plate can be literally considered as a certain area, right? Yeah. So in this case, the formulation will be, so let's say you have a thin plate represented by a certain region R. Then we can define a density function. Let's define density function delta xy. So you pick a point within the region R, you plug into the density function, then you get a density value associated with that location. Right. Then what we can do now is you pick a very small area, okay, in that around certain location, right? So you're interested in what will be the small mass, okay, associated with that little patch. And that calculation is also very straightforward. Because it's a very small patch you have selected, we consider the density within that little area is constant. So let's say you selected density around the location x, k, y, k. Okay? Then the density is delta of x, k, y, k. So that times the little area delta A, okay, to give you the mass of this small area. Then your total mass, right, will be the addition of all of the small mass. So let's call this I, let's call this as K here. And of course, K goes from 0 to N. K goes from 1 to N. Right. Now, as N goes to infinite, so the summation sign basically become, this is approximate. The summation sign become double integral. And then delta mass here basically becomes delta xy times dA. And you're integrating over the region R. So now you get a double integral. Right? So this double integral here, what are you integrating? You're integrating a function delta representing the density. Even though this is a symbol delta, basically this is a function f, right? Same meaning. And you integrate it over the region R, integrate the density times the dA, then you get a total mass of the thin plate. So really, this is just a double integral, right? You're just giving it a meaning for this double integral in terms of mass now. And you see, remember, this is how we cover double integral. Remember when we start double integral, we actually talked about is what's the volume below certain function and above the region R, right? So we end up with the double integral formula. So basically this formula here can represent a volume underneath the surface F and above the region R. And the same equation, right? Same mathematical expression. Now you can actually interpret it as a mass of a thin plate, as long as the function f is being replaced with the physical meaning of a density. So it's all up to you how we make use of this mathematical function. So that's the second application. Our third application is to calculate the average value of this function over a region R. Okay, so average value of this function over region R. So let's take a look at how we interpret this application here. So let's start from a simple case. So recall if you have a data set, A1, A2, up to AN, okay, n number of real numbers, and we have learned, okay, how to calculate the average. So what you do is you add up all the numbers and you divide it by n, so you get the average value, right, based on the data set. Okay. So now I'm going to translate this average concept into a double integral. So here's what we're going to do. Okay. Now let's consider a surface or function, okay, z equal to f of x, y, and a region R. Okay. Okay, so here's a surface, and here is region R. Good. So now, if I pick a point within this region R, so let's call this point xk, yk. Then, if you extend this point up until it arrives on the top surface Z, so over here, right, then you get zk equal to f of xk, yk. That's the value, okay, on the surface here. Or this refers to what? Refer to the height, right? From this point on the surface to the location of x, k, y, k within region R. Okay, so that's basically, this is like a height over here. And then you can try another location. Okay, you do exactly the same thing, and you will get another height. It's or another value of function f at that location, right? So basically, there are so many different points within the region R. Okay? So what you literally can do is you can pick n number of them. Right? So let's pick n points, n locations. Each location give me a value based on the function f. So you add up the n number of locations, right? So you're adding like an n height, n number of heights. This is what happens here. And then if you divide by n, right? So then you're supposed to get an average height, right? An average height defined by the function f within the region R. So that's getting to somewhere like this meaning, right? Average value of this function over region R. Okay. So this one here alone, okay, it's not quite enough yet. So basically, if I had to write it down here, so this is, so let's say this is approximation, okay? Average height or average value of f over this region R, this expression here. Okay, so now I'm going to manipulate this expression. Manipulate means I'm not going to change that. I'm just going to adding, subtracting, or multiply or divide, okay, that kind of things. So we're going to multiply delta A to this expression. Okay. So then if you multiply delta A at here, then you have to multiply delta A on the denominator so that they cancel each other. And then we're not changing this expression, right? Okay, so then what is n times delta A? Delta A is, right, let's say you have a small area here, right? It's like you have a small area associated with each one of the location. Then n times delta A will actually be approximately what? Approximately be the area of the region R, right? Okay, if you use n times delta A. And so that's approximately 1 over the area of R, and then multiply by the summation sign. Okay, good. Yeah. So now I'm going to let this n go to infinite. Initially, we're just taking n number of points. So now expand to infinite. Okay. Infinite, so of course, there are infinite number of points within the region R. So once you do that, then this is still the average height or average value of the function f. Once you n go to infinite, then n times delta A basically becomes the area of R. And summation sign becomes double integral. And you're integrating this function, and delta becomes d, right, dA. So now you got an expression in terms of double integral. And the meaning of that for this expression is the average value of the function f over r. So you could replace h with f, the same meaning, right? So average value of the function f over the region r. How did you get that? You integrate the function f over r, then divide it by the area r. Right? That's the end result. Okay. So let me show you an example here without doing this. You know, we've done double integral, so there's really nothing tricky in terms of computation. It's just application, right? So for example, let's say here's a question here. Given a region R, okay, and then also given a temperature, a temperature function T of xy. So this T of xy represents temperature distribution across this thin plate region R. You pick a point within region R, you plug in here, you get a temperature, right? So a question that you can actually calculate is, then what is the average temperature? Average temperature over this thin plate R. So how do you calculate? You use that formula here. If you have the temperature distribution capital T, and all you need is just integrate it over this region R, divided by its area, then you get the average temperature over the region R. And that's application. Okay, good. Yeah. So another application, another example is this. So let's say you got a region R and a point P. So here's region R, here's a point P. So you have the point P given. So I don't know, maybe, 2, 3, or 4, 5. So basically the coordinates of the point P is given. Okay, yeah. Then a question can be, what is the average distance, okay, from point P to region R? Right. What is the average distance from this point P to region R? So region R, distance means if I pick a point within this region R, then you can get the distance. You pick another point, you get another distance. So we're trying to get the average distance from the point P to this whole region R. Okay. So how do I formulate this problem here? So remember, this P is a known, right? This is known coordinates. So you have a known coordinate, okay? And then all you need to do is first, so let's let f of xy represent the distance from point P to anywhere within region R. Okay. So you can let it to be a distance from point P to arbitrary point within region R. Essentially, if point P has a coordinates, let's say x, p, y, p, then what's the distance? So f of xy should be square root x minus xp square plus y minus yp square. Right? That's how you calculate the distance between two arbitrary points. Okay. So now, if you're trying to get the average distance from the point P to the region R, then all I need to do is to calculate using this formula. right? So that formula give me that equal to 1 over the area R, double integral, the function, the distance function, and over this region R. Okay, so exactly same expression in terms of double integral. Now you're giving the function a different meaning, and you get a different physical meaning back. Right? Okay, that's how you would use this formula to calculate the average value of a certain function. Okay. So without giving you the actual numbers, I think once you get this kind of question, you just have to formulate it properly. Any questions on this part? Okay, good. All right, so now let's extend it a little bit, right? The previous bullet point is the average value of a function over region R. So how about weighted average? Okay, weighted average. So let's take a look at the concept of weighted average. Okay. So in statistics, you have already learned weighted average concept. Okay. So weighted average of function f of xy. Okay. Again, let's start from the simple concept from your 254. Okay. So suppose you have a data set, same data set, A1, A2, and up to AN. At the same time, you also have a set for the weight, W1, W2, Wn. Okay. So the weight, W1 associated with WA1, W2 associated with is A2, and Wn is associated with AN. Okay. Then you can calculate the so-called weighted average. Let's call it X, let's call it A bar here. Okay. And then you get what? W1, this weight times A1, W2 times A2, Wn times AN. So you multiply the weight with each one of the data in the set. Then you divide it by the sum of the weight or the total. Okay. Then you get this so-called the weighted average. Okay, yeah. So how can I relate this to a double integral concept? Okay, so remember the bullet point here is the weighted average of a function f like this. Okay. So now let's consider f of xy. Consider we have a function f of xy at here and a region R. Okay. So again, here's your surface or the function on top, and region R is at the bottom. Okay. So we're going to have one more condition in here. So you have a function here, you have a region R here. Suppose this region R actually represents a very thin plate, metal plate. Okay. So now let's say I also know the density, okay, delta xy, okay, for the region R. We got three things working at the same time. Okay. So how do I interpret this? So basically, say if I pick a point at here, so xk, yk, and you can create a small patch, right? You call it delta A, little area around that location. And if you extend this point upwards, then you get f of xk, yk. Okay. In bullet number 3, we calculate this average value of the function f by taking n number of them, right? Then you let n go to infinite, you get a double integral. Okay. So now I'm going to do one more thing here. So essentially, in the previous case, you just multiply this function with delta A. But then in this case, I'm going to multiply this function with a small mass representing this delta A. And that basically means the delta, it's the small density, it's the density at the location times the delta A. Right, so this delta mass here is basically this one here. Okay, so now you can easily see the weighted average okay, the weighted average is F bar here. It can be written as, let's say if I have n number of them, okay, then you have a f xk yk, so this value here, then times the delta m here, so times xk yk delta a, right? So this is your delta mk. And divided by, right? So this is your weight. Basically, this quantity here is considered as the weight. Because you're multiplying this function, which is a value, with another value represented by delta mk. And then you add them up. Right? So it's like what you're doing here. So this quantity represents the weight. This quantity represents the data set. Then divided by the addition of the weight. Right. Exactly same format. Right? So your total on the top divided by the total weight, and you get the average, weighted average value at here. And finally, you can let n go to infinite. Once go into the infinite, all of the summation sign becomes double integral. So now you're integrating a function in this format. And the bottom here, you're integrating like this. Right. So you get a new expression, and this new expression at here, essentially you're calculating two double integrals, but now they actually have a meaning. It's the weighted average of the function f. So you can shy away from the mass concept. Over here, you can see, okay, so the function f is weighted by this quantity, right? Then you're getting the weighted average here. But the bottom line, also you can also consider, right? The denominator at here, okay? When you calculate, if this is a density, then the denominator actually give you what? Give you the mass, the total mass of the thin plate, basically. So the next time, when you see an expression like this, okay, and it actually should draw, okay, that actually give me the weighted average of this function f. So what is the weight? The weight is the delta function here, right? Okay. So that's the idea of a weighted average. It's all good. There's throwing a lot of formula at you, but none of the formulas should be strange because there are new formulas, but none of the formulas involving any new computations, right? They're all double integrals basically. Okay, so the next one is center of mass for a thin plate. And this is an application based on the results directly come out of the number 4, Boolean number 4. So how do we get the center mass for a thin plate? Okay. And this is a very useful mechanical quantity. If you do mechanical engineers, civil engineers, right, you deal with this center mass probably a lot. You need the information center mass to do your calculation. So let's suppose this is a region R representing a thin plate. And it has a density. It has a density given for the thin plate. Okay. So center mass basically means you're looking for a so-called average value, okay, for the X and average value for the Y. And that's what you're looking for in terms of center of mass. So what does average value, right, of X or average value of Y means? Okay, so for example, if I pick a small location right here, okay, so then you have this location, okay, reference to the Y-axis, okay, you have this much distance X, right? So if you pick another location and you have another distance of X. Okay, so let's say this is X1, this is X2. Okay, and that's purely determined by the actual location of that point within the region R. Okay. And however, right, the key here is there is a density function associated with the thin plate. So technically, the density at each one of the location could be different. Or in other words, if you consider this location here has a very small mass, differential mass, and then there's differential mass around this location, okay? And they can be different, and they can be determined by the density function here. So then the question basically is, if I need the average, then it becomes the weighted average. Right? So your X1 is weighted by the mass at that location. X2 is weighted by the small mass at that location. If you can get the weighted average, then you get this X bar at here. Okay, so that's the idea, right? So if I have to use the formula that I have derived here, you see this is exactly the formula. The formula says you calculate the weighted average of function f by doing this computation. The function f times what? This is basically your dm, right? Your small mass set it there. So this is a function times dm, and then divided by the total mass at the bottom. So if I use the same analogy here, the x bar, if I need to calculate the x bar at here using the formula, all I need to do is to replace the function f with what? You're weighting the x with dm. So you basically replace the function f with x, right? X is the coordinates, and you have different coordinates. And you weight this x with the small mass. So that's delta xy times dA. And then you divide by the total mass. Right, so now you get the average, the weighted average of the x coordinates. You get the x bar. Similarly, you can get the y bar by doing the same operation, except you're weighting the y coordinates. Okay, right, now you get the y average value. Okay. So the two expressions out here are actually quite interesting expression. The first expression, we can define the numerator as a so-called my. And the second expression, we define it at mx. There's a reason. You might wonder, why is it called my? Why is it not called mx? So just hang on a second here. So you can define basically this double integral as my and define this double integral as mx. Okay, yeah. So if I had to rewrite it here, basically your my, right, equal to x times delta xy dA. Okay, so this little portion here, right, as we have just iterated, this little portion represents a small mass, a differential mass, delta xy times dA. Okay. So then technically what we're doing here, in terms of my, the calculation, okay, is this. Suppose this is your region R. Okay. And then here is the location you're interested. If this location here has a dm, and then this location has a corresponding distance to the y-axis. So that location to the y-axis is represented by the x coordinates, right? Yeah. Then here, the integral here, what you're doing is you're using x times the dm, right? So basically let's call this a delta. So you're using x times delta m, or let's write it the other way. Basically delta m times x. So that's what the integral is doing here, right? You multiply x with this, or multiply the delta m with x here. So there's a name for this, right? So remember, how do you calculate how do you calculate the moment due to a force? What do you use? You use the value of the force times the distance, right? The short distance from the force to the pivot points. Okay. So now what we're doing here is essentially you look at the formula, is you're using this little mass times the shorter distance to the y-axis here. Okay. So that's why the my, this term here, there's a name associated with it. Okay. So this is called first moment of the area, okay, with respect to y-axis. Okay. So this delta m represents the mass of the little area. So it's a mass moment. It's a mass moment concept. And in analogy to force moment. Right? It's never heard of mass moment, right? We never saw it, but this is actually quite a useful concept. I think in statistics, you also have a mass moment, basically concept, because basically first moment, you can get the average value. So next time, right, this is called the first moment of the area with respect to the y-axis. And the average, the center of mass, x bar, y bar at here, right, could be interpreted as the first moment of the area with respect to y-axis divided by the total mass. This is very mechanical or civil related concepts. Right. So I'm kind of running out of time here, but there's one more bullet points, which is one more application. It's also a very important application, is moment inertia. Okay. But because this is a double integral, because this is the region R, so we're actually looking at a moment inertia of the area. Okay. Because it's a thin plate, it's not a actual 3D object yet. So after we learn the triple integrals, okay, then we can actually get the moment inertia of a 3D objects. Okay. But the idea is exactly the same thing. So next lecture, we're going to cover this. How do I get the moment inertia specifically moment inertia of the area represented by the region R. Okay, so let's take a look at the next lecture together. Okay. All right, so any questions, feel free to come over. Yeah. Sure, just give me a sec, let me stop the recording.